Our next talk is Thomas Fenster from UC Davis with Patty Oikawa from Cal State East Bay. So if you guys want to share your screen when you can, yeah, awesome, thank you. And take it away when you're ready.
1 second. Okay, can you guys all see that?
Yes, thank you.
I'm Patty Oikawa. I'm going to start out this team talk and then hand it over to Tommy Fenster, and Housen is also going to speak for a little bit here. But we're going to give an update on our investigation of compost applications to grasslands as a climate mitigation practice. And let's see. So as we all know, it's going to get very difficult to get to net zero by 2045. So we're going to need some amount of negative emission technology, and a lot of focus has been put recently on these nature-based solutions. There's a recent paper in PNAS here, which was highlighting a lot of diverse types of practices that we could use for the state of California in particular to help get us to our goals of 2030 greenhouse gas reduction goals, and they assessed it could get us almost 20% of the way there. And this is involving reforestation practices, wetland restoration, but also compost amendments. And you can see compost amendments to grasslands are actually give you a pretty small carbon sequestration benefit here relative to some of these other practices. But the strength of this mitigation practice is that grasslands cover a large surface area. So when you scale this up, it could make a big impact. So 30% of the global terrestrial land surface is grasslands. And for California, it's even more than that. It's about 50%. It's also a good potential ecosystem to work in because it tends to have degraded soils and from overpasturing for long periods of time. And then a more recent estimate suggested that if you were to scale these compost amendments to 50% of the rangelands in California, it could capture up to 30 million tons of CO2 equivalents per year. So this could potentially have a large impact for us. What is the compost mechanism? So the whole idea here is that you add compost to the surface, and that acts as a slow release fertilizer and a source of carbon for soil organic matter creation. And previous studies have kind of tracked this carbon through the soil and shown that it can get sequestered into soil aggregates and physically protected, so potentially staying there for long periods of time. The increased SOM also can lead to increased soil water holding capacity, which can help with drought resilience. We're having a big drought in California right now, and improve soil health. So a lot of this work has been pioneered by Wendy Silver's lab at UC Berkeley, and she's done a lot of studies on this. But generally what her finding has been is that when you apply this one-time application of compost to grazed grasslands, and it's a very small layer that you put on the surface, you capture around 2 metric tons of carbon per hectare per year. And this is showing all of the different grassland sites that they've studied across the state and some of their old sites versus their new sites. And it's really this kind of repeatable result of around 2 metric tons of carbon per hectare. And they've done some modeling out into the future. Some of these sites have been monitored for 10 years, but they've done some modeling thinking that it could be maintained for up to 30 years of this enhanced carbon sequestration. There's also really huge co-benefits of this, of sort of recycling and upcycling our waste streams, reducing landfill and manure storage loads and those associated emissions with storing manure and all the methane that can be released. So those are kind of the take homes from that. And then also I just wanted to pause for a second and just frame this study, which is part of a much larger grant given by the California Strategic Growth Council And so we're just one part of this larger team that is looking at soil amendments in general. So not just compost, but biochar and rock amendments to rangelands and also row crops, almonds, olive orchards, et cetera. So we have 27 demonstration sites across California. And the LBNL team is really leading up sort of the upscaling and the modeling tests of these different types of amendments. Okay, so now I'm going to pass it over to Tommy Fenster.
All right, thank you very much, Patty. So in this slide, I'll go over a little bit of our design. So we installed the tower in the summer of 2019, and we essentially had a year and a few months of baseline data with which to collect. In October of 2020, we applied compost to approximately 4 acres of the grazed grassland site. And if you look at the figure 2 down here on the bottom right, the compost application area is the 4 acres outlined in red, essentially right here. And then, so that's our compost application side. And within this compost side, we also broke it into a series of plots from which we would collect our plant biomass data, do chamber measurements, and also take soil carbon measurements. And we had the same corresponding plots over here on the control side. And then what we did post-compost application was compare fluxes coming from the compost area to the control area. And what we used were the Clune model of half-hourly footprint models as sort of our first way of comparing these fluxes. So any footprints at least 70% or more were in the compost area, we defined as sort of treatment area, compost area fluxes, and 70% or more in the control area we defined as control fluxes. So that's how we did our comparison. We also had 2 Phenocams set up. Phenocams looking at the greening up of the control side, and Phenocam looking at the compost treatment side. So let's see, moving on. Oops. Excellent. So initially thought it would be nice, potentially if we had similar years meteorologically to do kind of a before compost, post compost application. But as you can see from looking at this figure, that really wasn't possible. Moving in to the 2020 year, we got significantly less rainfall than we did in that 2019 year, and correspondingly a good deal less soil moisture as well too. So really not necessarily allowing that post compost application, but also showing the large amount of variability that can occur year to year in these sites. Moving on. So looking at the overall tower footprint, somewhat unsurprisingly, when you look at the difference between the 2 years, you can see the reduced rainfall really corresponded to significantly less GPP and respiration. The amount of cumulative NE was about the same, but just the amount of growth and biological activity was just significantly less in the second year. This red line here indicates when the compost was applied in October of 2020. So really, for looking at the effect of this compost on the site, really needing to simultaneously compare the areas where the compost was applied to the control areas where the compost was not applied. So that's what this figure shows here. We have the data representing the area where the compost is applied on the left, and the area where the control side on the right. Our top figure is our NEE with the gap fill in gray and the actual measured data in black. Going down to the second panel, we have our GPP in gray on the bottom and our respiration in black above. And going down to our final slide, we have our cumulative sums of GPP in green, and then respiration in red, and then NEE in black. And really, the really fascinating thing that we saw was post this compost application, we saw that the GPP is higher, and it starts sooner. You can see that down below, and also in the cumulative green line as well here, and that the respiration is also significantly higher in the treatment side, which the result of this higher respiration completely kind of cancels out the increase in GPP that we saw. And if you're looking over at the control side, you saw maybe a slight negative sink in there, but a good deal less respiration and GPP happening in the control side. And how we got this kind of higher GPP is a really interesting observation we made. I'm going to hand it off to Housen now to discuss that aspect.
I'm going to quickly just talk about our Phenocam before we go to Housen, but just quickly, the Phenocam data we're showing here, starting in 2020, going through 2021, this is GCC from the Phenocam Greenness Index, and this was when we applied compost. And you can see here on the treatment side, the green up started a whole month, 30 days earlier than the control side. So pretty shockingly different phenology. And you can see in the photo here, this is sort of the line of where the compost was applied on the right compared to the control side. So it's visibly, we saw it in our field notes, so it's a lot greener sooner. But the senescence was the timing of the senescence and the trajectory of the senescence was the same. So it's actually just a longer growing season, and earlier green up for the compost side.
Yeah, so it's important to recognize other benefit about this compost application, especially highlighting the previous presentation. So like a biophysical feedback, right? So as Patty just mentioned about the earlier phenology of this compost application side, we also noticed the energy partitioning and also evapotranspiration are much different at this side of the field. So you can see here, I'm showing the response function of the LE against the potential LE. So this is a kind of a model based on Pemberton-Maltese equation. Check the poster if you want to see a detail. And also sensible heat against the incoming radiation. During the early growing season, as pointed here on the top right of the trajectory of the phenology, you can see the higher LE and also lower sensible heat during this early growing period of time, especially for the compost part, the red one. And next slide. But the difference diminished later into the growing season when both fields are greening up and also showing a very similar vegetation property. So this again highlighting the importance about measuring and also starting this co-benefit of this climate solution. So moving back to Patty.
Okay, just one more data slide here. This is Isabel Torres's work. She's a master's student in my lab and heading up the chamber measurements of CO2 and methane fluxes. And so again, the treatment soils are in red and control soils are in blue. And sort of the interesting thing, again, this is the compost application. We've seen sort of consistent and negative methane fluxes, so a lot more uptake of methane in the treated soils compared to the control soils here, which are in blue, are just very much zero throughout this whole period. And also that respiration signal that Tommy mentioned earlier is there's more respiration coming out of the treated soils compared to the control. So this is really interesting. Another thing that's kind of interesting here is it's sort of the reverse of what we're seeing with the soil moisture here, is when we get higher soil moisture following a rain event, we have low methane uptake, but then as it kind of dries down, we get a spike in methane uptake, and then it kind of is the mirror image of the moisture. And so we're going to be doing a deeper dive into this and actually looking at some of the PMOA genes, which is a very characteristic of methanotrophs in the soil, and using some quantitative PCR and seeing how the microbial communities have shifted. Amendment, we're thinking it has to do with nutrient availability in the soil. Okay, so just to summarize, we our kind of three main findings was that there's large impacts on the phenology of the ecosystem, which is a new finding. Again, like Housen was saying, these are scale emergent properties and previously unaccounted for in models. It's not just an earlier green up, but a longer growing season, which has implications for water cycling and land managers. Our higher plant productivity, high GPP, was completely offset by high ecosystem respiration. It's going to be interesting to track this into our second year here and see how those dynamics play out in year 2. We're also going to be analyzing our soil carbon and nitrogen data and looking at what's happening deep in the soil, and then following this methane oxidation soil as well. So that, I'd just like to thank our funders, and we are out of time. Thank you.